All right. Hello, everybody. Welcome back to Math Background for Machine Learning. So today we're just going to continue with the material on propositional logic. Um, so uh, just checking, yes, the microphone is in fact on, and I appear to be streaming. So that's all good. All right. So. All right, so last time we talked about propositional logic, and we went through basically the representation of formulas of propositional logic. It's pretty simple. All of the variables are either true or false, and you can connect them with connectives like and, or, implies, not, that sort of thing. Um, so the more important thing, the more complicated thing, is proofs in propositional logic. So we don't just want a way to express formulas of propositional logic. We want a way to argue that they're true. And so I spent the second half of last lecture discussing inference rules and proofs for propositional logic. And so just to review, a proof is basically, you can write it in what's called two-column format, where you have a sequence of statements, one after the other, and next to each statement you put a justification. And the justification is one of two things. Either it's an assumption or it's one of a well-defined set of inference rules. So for example, modus ponens is an inference rule. And the nice thing about writing down an argument this way is that you can check it very easily. Like if the argument checks out, if all of the statements are either assumptions or follow from earlier statements by inference rules, then you know that the conclusion is correct as well. And so it's rare that you would actually be making a proof in propositional logic, but it's a great way to see the structure of proofs, to practice making an argument formal and to recognize when an argument isn't sufficiently formal and therefore might have a flaw in it. So in particular, at the end of last class, I did this exercise right here. Right, which is this one right here, which is basically, it's not a very deep formula, but it's an example of how to do a proof, right? And the proof was, I think I have it right here. Yes. Right here. So to prove A and B implies B and A, you make A and B as an assumption. Then you use the commutativity inference rule to swap the order, right? And then you close the lemma, right? So closing a lemma means collecting together all of your assumptions and putting them on the left of a inference of an implication sign, and then putting the conclusion, which in this case is this, on the right-hand side of the implication sign. And so this here, 3 lines, it gives you a proof of A and B implies B and A. And so that's an example of a formal argument. And so what I'd like to do is just complete our discussion of propositional logic, because it's nice to have sort of a complete understanding of this one simple formal argument system, and then talk a little bit more about proofs in general and how they fit into machine learning. All right, so I think the very last thing that I talked about, but I'll go over it again, is negation. We gave a list of inference rules, right? So modus ponens was our first one, and then there's a whole bunch of other inference rules that I listed out here. All of these inference rules, they they make logical sense if you stare at them. I'm not planning to go over all of them in detail, but if you have questions about any individual one, please feel free to ask them on Piazza. Let's see. And so just to get a complete set of inference rules for propositional logic, we have to have some inference rules that deal with negation. And so the simplest way to deal with negation is what's called constructive logic. And in constructive logic, all you do is you define negation as a shorthand for this, right? So not phi is a shorthand for phi implies false, right? In other words, not phi is true precisely when phi would lead to a contradiction. And what I mean by lead to a contradiction is that if you know phi, and you know not phi, which is this, modus ponens lets you conclude false, and concluding false is basically a sign that everything has gone wrong, and you've assumed some contradictory things in your proof. Okay, and so at that point we can just stop there and say we have a complete system for doing proofs in propositional logic, and this turns out to be actually quite a nice system. But it's not the system that is most familiar to most people. So let's keep going and talk about additional ways to handle negation. So the most familiar system to a lot of people is what's called classical logic. And classical logic gives you one additional inference rule, or I guess a family of inference rules. It's one inference rule that lets you conclude a family of statements, sorry. For any statement phi, you can conclude phi or not phi, right? So that's called the law of the excluded middle, meaning that there's true and there's false and there's nothing in between them. And that holds in classical logic and not in constructive logic. And so if you want to, then you can make a proof completely with the law of the excluded middle and then the inference rules that we've talked about previously. There are also a bunch of other inference rules that people have devised for negation, and they are equivalent in the sense that you don't need them. They're just convenient to have because they make proofs shorter. So De Morgan's laws, right, is basically that if you have negation outside disjunction, you can push it in and flip the disjunction to conjunction. And the same thing, if you have negation outside a conjunction, you can push it in to each of the conjuncts and turn the and into an or, right? So De Morgan's laws basically just tell you that you can move a not inside either an and or an or by flipping whether it's an and or an or. Double negation elimination, if you have two negatives, then that's equivalent to a positive. You just delete the two consecutive negative signs. And contraposition, phi implies psi is the same as not psi implies not phi. So any one of those are legitimate inference rules, and we would typically just use whichever one of them is convenient. But if you're interested in an exercise in logic, you could try and derive one of them in terms of the other ones. So that completes classical logic, classical propositional logic. And so, that's kind of, it's a nice system. It's like a contained system that is complicated enough that you can do real proofs, but simple enough to actually understand those proofs once you've done them. I want to mention there's one more inference rule that people often use in classical logic, which is resolution. And you might run across it. It's more common in classical AI than it is in machine learning in general, but it's worth knowing about. So resolution is a inference rule that looks like this. If you have two formulas of the form phi and chi and not phi and psi, right? So phi appears in both formulas, positive in one and negated in the other. If you have something like that, then you can, sorry, this is an or, let me say that again. You have phi or chi and not phi or psi, right? And phi appears positive in the first and negated in the second. And resolution lets you combine these formulas by deleting the phi and the not phi, and just adding, like, sticking the remaining parts of the formulas together with an or, right? And so it's worth thinking a little bit about why this is true. And informally, you can argue by cases. Suppose that phi were true, right? Then there would be no reason to put any constraint on chi, right? Because if phi is true, then phi or chi is true, and so chi doesn't need to be true in order to make this true. But on this side, if phi is true, then not phi is false, and so that means in order for not phi or psi to be true, psi has to be true, right? So in the first case, when phi is true, psi has to be true. In the second case, let's say not phi is true, right? When not phi is true, then there's no constraint on psi, but in order to make this side true, chi has to be true, right? So we now have two cases, either phi holds or not phi holds. In the case where phi holds, then psi has to hold, and in the case where not phi holds, then chi has to hold, right? And so putting the two cases together, one of those two cases has to hold, and so you have to have chi or psi, right? So that's an argument for why resolution makes sense, and you can in fact formalize that in a proof in classical logic. And that would be, again, another good thing to try out if you're interested. So specifically, resolution is really useful when you do it on clauses. So what is a clause? A clause is a disjunction like this one, where every disjunct is a literal, meaning just a variable or a negated variable, right? So this is a clause and this is another clause. And doing resolution on clauses, it's the same as doing resolution on general formulas, right? You can just take phi to be, let's say d appears positive here and it appears negative here, so you can take phi to be d, and then chi, right, is just the rest of this formula, a or b or not c or not e, right? And then this is not phi, not d is not phi, and so psi is just the rest of this formula, b or f, right? And so if you apply just literally this rule, just syntactically apply it, you get that the output of resolution is this clause, where we've taken all of the literals that were in this one except d, and all of the literals that were in this one except not d, and stuck them together with disjunction. I should point out that b appears twice, right? It appears once in this guy and once in that guy, and you only need it once in the final output. So that's another simplification, and that is commonly even included as part of the resolution inference rule. So why is resolution on clauses a good thing to know about? It's good to know about because it is actually exactly a, I think, here, let me hit reload on this, because I think I edited to explain this in that piece of the notes. Yes. All right. Oh, come on. Duo is useful, but let's approve myself. Apologize for that. All right, so where were we? All right, so here we go. So this is what I added, this parenthetical comment, that it's popular, it's useful, because it's the basis for a complete reasoning system, meaning a reasoning system that can find a true fact whenever, find a proof for a true fact whenever one exists. We're not going to cover that system in this course because well, it's a little bit complicated and we don't have time. But if you're interested, you can take our Grad AI course, which is, I highly recommend it. I used to teach it and I liked it when I taught it. So it was a cool course. Still is. All right, so that's classical logic. I want to mention one other thing about proofs in classical logic, which is scoping rules. So here is a proof that has some scoping in it. So what do I mean by this? So far, all of our proofs have needed just one lemma, right? They've been simple enough that you could do it with only one lemma. In more complicated proofs, you might need to introduce more than one lemma in order to get to your result. And in fact, you might need to prove a lemma, and then within the proof of that lemma, you might need to prove another lemma, right? So you might have nested lemmas. And so when we do that, it's convenient to actually indicate that scoping. And we can do that with indentation if we want to. Messes a little bit with the two-column format, but you can have shallow indents so that you still have space for the justification over on the right. So here, right, here's a proof where we have an outer lemma, and then within that lemma we do another lemma, right, from lines 2 to 3 in the second scope, and then within that lemma there's a third lemma, right? And in the end, we show this fact, right, which is, if I wanted to read it, I would say, if peanut butter and jelly make a sandwich, then if you give me peanut butter, then jelly will make a sandwich, right? So it makes sense, right? And it is in fact a true formula of propositional logic. And to prove it, you needed, multiple nested scopes. And so you treat these exactly like scopes in any programming language, right? Like you open a scope by saying, I'm going to start a lemma now. You declare assumptions within that scope, and those assumptions are true within that scope, and then they vanish once that scope closes, right? And then every time you end a lemma, you collect together all of the assumptions from that scope, right? And those are the left-hand side of the implication. And you have a conclusion within that scope, and that's the right-hand side of the implication. So we'll go through this proof in a sec, but I just want to make sure that I mentioned all of these things, right? So assumptions, it's the same thing as nested scopes in a programming language. You can see assumptions that were made in any enclosing scope, right? So up here, right, like I assumed peanut butter in this scope, and then in this scope here, right, I can still see that assumption because it's a nested scope. But once I end the scope here, right, I can no longer see my assumption of peanut butter. Yeah. So when I say just like a computer language, we will see exactly how much like a computer language it is. You can make a little Python mini language that lets you construct and check proofs, right? So here's a, going back to the proof that A and B implies B and A, here it is in Python. So you start your lemma, you assume A and B, and I'm doing it the second way that I described how to do it. So you do AND elimination to get A on its own, the zero argument of the AND. You do AND elimination to get the B on its own. That's the one argument of the AND. Because it's Python, indices start from 0. Then you can do AND introduction, right? So this thing proved A, this one proved B, and so you can do AND introduction on B and A, and that gets you the conclusion that B and A is true. And then you can end the lemma using B and A as the conclusion, and it automatically collects all of the assumptions, which is just this one here. I'm actually in a sec going to hand out and let you guys play with exactly this. But before we do that, let's go back up and so here is in text the description of how to read this proof, but let's just I'll just go through it step by step. So right, so we're trying to prove this statement at the end, right? This kind of complicated statement. So the first thing we're going to do is assume PB and J implies sandwich, right? And how do we know to do that? Well, anytime you want to prove an implication, it's a good idea to start by assuming what's on the left-hand side of that implication. So we'll assume PB and J implies sandwich. And then our goal will be to prove what's on the right-hand side of the implication. Okay, so we've assumed that, and now we have to prove PB implies J implies sandwich, right? And so that's another implication. And so to do that, we'll assume what's on the left-hand side of the implication, which is what we did here, right? And now our goal is to prove J implies sandwich, right? And again, that's another implication. And so we'll assume J, right? And now we've assumed all of the things that we need to assume, and we can start to prove the things that we need to prove. And I should point out, for each one of the implications that we want to prove, right? So to prove this implication, we started a new lemma, right? That's this line. And then to prove that implication, we started a new lemma, right? And then to prove that implication, we started our innermost lemma, right? So now, in the innermost lemma, our goal is to prove sandwich, right? So we've assumed J and we've assumed PB, and so we can prove PB and J by and introduction. Oh, and it looks like the number citations are messed up. I will fix those after class, but basically it's saying from this line and from this line by and introduction I can prove PB and J, right? Then PB and J I have, and that matches this assumption here. So by modus ponens, I can prove from PB and J, and from PB and J implies sandwich, I can prove sandwich, right? And so now that lets me end the lemma, right? I've assumed jelly, and I've proven sandwich, so I get to end the lemma and say that jelly implies sandwich, right? Now, I'm effectively done, right? Because now in the next lemma, I've assumed PB and I've proven jelly implies sandwich. And so I can say PB implies jelly implies sandwich, right? And then finally in the outermost lemma, I've assumed PB and J implies sandwich, and I've proven PB implies J implies sandwich. And so I can stick those together on either side of an implication sign, and that's the thing that I was originally trying to prove, okay? So this is a somewhat more complicated proof, and it shows you basically that by working with these sort of small, formal, easily checkable steps, we can build up some fairly complicated conclusions. All right. So I think now is a good time to do two different things. So I'm gonna pause the stream and take a look on Piazza and see if there are questions that need to be answered. And I'm also going to hand out the quiz for today. So I will I'll answer questions for a little bit and then post the link to the quiz. The link will be available on Canvas, and I'll also link to it from Piazza. So let us pause the stream and ask any questions that you like, and pretty soon there'll be a quiz. All right, so there weren't too many questions on Piazza, so I've just released the quiz for today. We'll pause the stream for another few minutes while people work on the quiz. So see you back in a few minutes. All right. Hello, everybody. We're back. Looking at the submissions, it looks like most people had time to finish the quiz, so that's good. As with the last quiz, I've set it so that it ends half an hour after the end time of the lecture at 3:30. So feel free to pause and keep on working. I'm going to talk now about the code that I just posted to Piazza. So if you look on Piazza, there's a new post here. I showed in the lecture notes basically how to make a simple Python interface for building and checking proofs. And so this should let you guys play with building and checking some proofs and hopefully A, give you practice, and B, give you a chance to ask us some questions. So I've put the documentation on Piazza, but basically what it is, it's an API that lets you build logical expressions and then build proofs using those logical expressions. So you can build literals, right, which are propositional variables. So if you just say literal of quote A, that gives you a literal whose name is A, and I've assigned it here to a variable named A, which it would be very confusing to assign it to a variable of a different name. You can build constant true and false. You can build expressions that say, you know, A and B, or A and B or not A, right? So each one of these, you know, this last one, Z, gives you the expression right here, right? So you did X, which is A and B, then you did Y, which is A and B or not A, and then you did Z, which is Y implies X, right? And right, you can build expressions that are true or false. It's, you know, your choice. And then we also gave some functions that let you build a proof, right? So you can start or end a lemma. Start lemma is, you know, it just opens a new scope for a lemma. End lemma closes the scope, and you give it an argument, which is the fact that you proved in that scope. So for example, here in this proof, we started a lemma, and then we ended a lemma later, where the conclusion of the lemma is B and A, right? You can assume a fact, and that puts it as an assumption in the current context. Fact is, in both of these cases, fact is a logical expression that you've built. And we've given you 3 more inference rules, which are and introduction, and elimination, and modus ponens. And they do hopefully what you would think they do. Have a look at the code for more detailed documentation. And then you can put these all together to make a proof. And so, you know, here's a simple proof. And if you just do this portion of the proof, right? So all but the last end lemma. You can show what's going on with this proof stack command. And if you run proof stack at this point, you get this. And it shows you all of the lemma scopes that you currently have open. So there's a global scope, which is always open. And then there's the scope that we started with start lemma. And in that, in this most recent scope, we assumed A and B. And we've proven A and B, right? Because that's proven because we assumed it. We proved A with the first AND elimination, so it's listed here. We proved B with the second AND elimination, and then we proved B and A with the AND introduction, right? And then we can end the lemma, and if we do that, right, if we add that, the proof stack goes to what I'm showing here, where we got rid of this whole scope, including all of its assumptions, all of its proven facts, and the only thing that remains is the implication that we proved by ending the lemma, right? So the implication has these assumptions on the left-hand side of the arrow, and it has a conclusion that we get to pick any one of these guys to be on the right-hand side of the arrow, right? And so here we told it to pick B and A, right? This last thing that we proved to be on the right-hand side of the arrow. So, so what do I want to say about this? It would be a good idea for you guys to play with this. We might potentially have an assignment related to it later. And so, let us know of any questions or problems that you run into while you're playing with it. Basically, the idea should be that if you want practice with proofs in propositional logic, this should let you write out a proof on paper and then enter the corresponding proof as Python code in your favorite Python interpreter, say Replit, and check that you got your proof correct, right? So it lets you self-check your proofs. So yeah, so give us, ask us questions if you run into problems with that. And I think that it's probably a good idea now for us to move on to a new topic. So what I'm going to do is I'm going to take I'm going to go through an example of a more complicated proof. So the specific proof system of propositional logic is not by itself all that important, right? Like, you can only prove facts of propositional logic with it, right? And a lot of times what we want to prove, you can't even state very well in propositional logic. So what is more important to take from it is this idea that you construct proofs formally, right? Where every statement, like, you give a statement and its justification, and every statement follows mechanically from its previously proven statements using the inference rule that you say. So what I was going to do is take a proof that you might see if you took 601, and I was going to go through it in a little bit more detail than we would typically go through it in 601, and give you guys an opportunity to ask questions about how it's put together, right? And so it's going to use a different formal system. In particular, it's going to use linear algebra. It's going to use a few other mathematical concepts that aren't included in propositional logic. But hopefully the analogy will be clear. You'll see that it's like a sequence of digestible steps, each one justified in terms of the previous one. So in order to do it, it's going to be a proof about an algorithm called the Perceptron Algorithm. And so first I have to define what that algorithm is and what it's for. So right. So let's say that we're given some data. And the data is a bunch of points in 2D, right? So we have some x's like this. And let's say that we also have another kind of point, which I'll write with O's, right? And so we have the positive points, which I'm calling x's, and the negative points, which I'm calling O's. And there is you can draw a line in between them, right? And so we can say that x's are on that side of the line, and on that side of the line it is all O's, right? So to make this more concrete, you might say that each one of these data points represents a flower that you looked at, right? And the x-axis is how long the largest petal is on the flower, and the y-axis is how wide the largest petal is on the flower, right? And so the positive examples are flowers of one species and the negative examples are flowers of another species, right? And it's your job to make a computer program that learns to distinguish species 1 from species 2. Okay, and so what you're trying to do, right? So this line, you can write it as ax plus by plus k is equal to 0, right? That's the equation of this line right there, right? And so x and y are the coordinates, and a, b, and k are coefficients that we have to figure out. And this kind of picture here, this is called a linear discriminant, right? It's a line that discriminates between the two classes. And the perceptron algorithm is a way to learn this linear discriminant. So I'm going to rewrite this same equation in slightly different notation, which is I'll take a vector x, y, and the constant 1, right? And the dot product with my coefficients, a, b, and k, is equal to 0, right? So this is just mathematically equivalent to that. X, y, 1 are going to be, they represent one of our points, right? The x coordinate, the y coordinate, and then the constant 1 that we tack on to make this equation work out. And a, b, and k, this whole vector, three-component vector, is a vector that I have to learn. Okay. So, right, so that's a linear discriminant. And we're going to assume for the purposes of discussion that there exists a perfect linear discriminant. We can get it so that all of the x's are on that side and all of the o's are on the other side. And that's, you know, in practice not usually true, but it's going to make the proof simpler, and so we'll go with it. All right, so that's the setup. We want to learn a linear discriminant. The perceptron algorithm is very simple. So we have, it's a streaming algorithm. So we see our data points one at a time. So we see, you know, xt, well, let's actually just say x1, y1, 1, right? That's our first data point. And actually, we also get to know whether it's a positive or a negative. So let's say it's a positive. And then we have to, before we know whether it's a positive or a negative, we have to predict, and then we see it and we get to know whether we made a mistake. And then we see the next data point, x2, y2, 1, and we have to make a prediction. And then we get to find out whether we were right or wrong. So let's say this one was truly negative, right? And so forth, right? And so we're learning our sequence of coefficients, a, b, k, right? We're learning our three coefficients, a, b, and k. And you know, we initialize them to some value before seeing the first data point. Maybe we initialize them all to 0, and we predict according to the sign of x1, y1, 1 dot our current value of a, b, k, and we decide whether to predict 0 or 1, positive or negative. And then we get a chance to update a, b, and k based on our based on whether we were right or wrong, and then we see the next example and the process repeats. All right, so we keep seeing a sequence of data points that looks like that. And what the perceptron algorithm does is it will initialize a, b, and k. It'll initialize them all to 0. And then for t equals 1, 2, forever, right? We see xt and yt, right? We predict the sign of xt yt1 dot our current value of a, b, k, right? And here there's an ambiguity, right? If this dot product is 0, the sign is 0, and we have to predict either positive or negative, and so we can break ties arbitrarily. And then the perceptron algorithm updates. So if we made a mistake, then we will set A, B, and K to be A, B, K plus xt yt1 if the example was positive, and the same thing, except it'll be minus that if it was a negative example. Okay, so hopefully the perceptron algorithm is clear, right? We just iterate over data points. We see the data point without the label. We predict according to our current vector of coefficients, and then on a mistake, on every mistake, we'll update our vector of coefficients. If we made a mistake and the point should have been positive, we'll add the current example. And if we made a mistake and it should have been negative, we'll subtract the current example. All right. And if you're interested, you should think about why this makes sense. Basically, if you add the current example, then you're more likely to predict positive the next time you see that example. And if you subtract the current example, you're more likely to predict negative the next time you see the current example. And you should be able to convince yourself of that with a little bit of algebra. All right, so this is the algorithm, right? The perceptron algorithm, and it works for learning a linear discriminant function. And so what we would like to do is prove that the algorithm works. And let's see, we won't be able to finish the proof, but we should at least be able to get a good start on it. So let me think about how far we can go. So let's see. Let's give names to each of these things. So in this sign, we break ties arbitrarily. I'm going to call this thing UT, and I'm going to call this thing WT, right? So WT is our weight just before we predict the teeth example, or when we predict the teeth example, and UT is the teeth example as a vector, right? And so let's see. So what we're going to do is we're going to suppose that there exists some, so we're going to assume that there exists some vector W star that makes 0 mistakes. And what we're going to prove is that the perceptron algorithm makes no more than a bounded number of mistakes. And we're going to write yeah, actually I think that's good. So on a mistake, what's going to happen? On a mistake where it should have been x, right, we're going to get that wt plus 1 is equal to wt plus ut, right? That's just this equation right there. So what we're going to do is we're going to take the dot product of both of these sides with w star. So we'll get wt plus 1 dot w star is equal to wt dot w star plus ut dot w star, right? We know that ut dot w star sorry, I'm going to make a slightly stronger assumption. Not just that it makes, well, okay, so it makes no mistakes. So that means so w star makes no mistakes. That means that it gets every example correct, right? Meaning that ut dot w star is bigger than 0 for everything positive, and ut dot w star is smaller than 0 for everything that should be negative. And I'm just going to make an assumption that says that w star is scaled so that the smallest possible dot product that it can have with an example is 1 for positive ones and -1 for negative ones, right? So let me actually just write that assumption. Write out that assumption here. And then same thing, assume w star dot ut is less than or equal to -1 for all of the negative ones, right? So this is a more specific version of the assumption that w star makes no mistakes, right? Because we can always just scale w star so that, right, everything is at least, it can't be 0. It has to be positive, strictly positive, or strictly negative for the positive and negative examples. So we can just scale up w star so that the smallest positive example has dot product 1, and the least negative example has dot product -1. All right, so this is the specific version of our assumption. So here, go back to this. Wt plus 1 dot w star is equal to this. And we know that that is greater than or equal to wt dot w star plus 1. because why do we know that? We know that ut is supposed to be positive, and w star dot ut is therefore bigger than or equal to 1, and so we can replace it by 1 here, right? All right, then the same thing is going to be true for a mistake with a negative example. So on a mistake with a negative example, we get that wt plus 1 is equal to wt minus ut, right? Again, that's just this, right? It's this line right here. And so we get that wt plus 1 dot w star is equal to wt dot w star minus ut dot w star. And here, now because we know that ut should be a negative example, we know that this dot product is less than or equal to minus 1. And so again, we get that this is greater than or equal to wt dot w star plus 1. So the same thing is true in both cases of a mistake. So on every mistake, wt dot w star has to increase by at least 1. Right? And that means, therefore, after if we make m mistakes, then our current value of wt dot w star is, this is a t, is greater than or equal to m. Why is that true? That's true by induction, right? It starts at 0 mistakes, and then every time we make a mistake, it increases by 1 at least. And so after making m mistakes, it has to have increased by at least m. All right, so that's not a complete proof, but I think it's probably a good idea to stop here and continue this next time. So because the next sort of chunk of the proof would take longer than till the end of the class. So yeah, feel free to, I'll post this PDF on Piazza as soon as I get a chance, and feel free to ask questions about it and you know, about anything else that we've discussed in the class. So I'll see you guys next time, and thanks a lot.